Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's get started on lesson 4.1.2, making scale drawings and understanding how scale works within drawings. Maps are examples of scale drawings. They are reduced versions of the original regions. A map is similar to the original region because it has the same shape. Because of this, maps conveniently allow users to determine distances between 2 points. In a scale drawing, it is important to decide on the unit of measure. Maps made in the United States usually will represent distance in miles, but they certainly cannot use actual miles of the unit of measure, right? You can't have a map that you unfold and have the map actually be miles long. So otherwise, a Pennsylvania map would be over 250 miles long and 450 miles wide. A map includes a scale which allows the units in which the map is drawn, or which shows the units in which the map is drawn. So here you've got an example of 5 miles on the map might be the same as 1 inch in real life. And so this is an example of us taking a drawing and making sure it is proportional or similar to the original, whatever the original is, and still making it look like the original, just a much smaller version of it. So it says, suppose, I'm not heard, Eulalia uses a map of Pennsylvania to determine that Valley Forge is 14 miles from downtown Philadelphia. Did she really measure 14 miles? Explain how she probably determined the distance. Okay, so remember, we're talking about a situation where we've got the scale where you've got from here to here is 1 inch, and that 1 inch is the same as 5 miles. So she uses a map of Pennsylvania to determine that Valley Forge is actually 14 miles from downtown Pennsylvania. So if I were to take this, and let me go ahead and group those guys together and do a cloner. There we go. So we would know that, let me go ahead. Actually, let me pause this for a second. Okay, they are my representations of downtown Philadelphia and Valley Forge. They are a certain distance away on the map. And since the scale on the map says it was a certain distance apart, it's 5 miles is 1 inch, we can go ahead and we can take for every inch that we measure from this location, which is considered downtown Philadelphia, that's 1 inch. Here's 2 inches. And it's not quite 3 inches away, right? 3 inches would be a total of 15 miles away. So it appears as if right here, X marks the spot, that's where Valley Forge is. And so we're able to go 1 inch, 2 inches, and it looks like it's 2 4/5 inches away on the map, and that would be equivalent to 14 miles in real life. So how could we use proportional reasoning to figure this out? Well, if you said that 1 inch is equivalent to 5 miles on in a ratio, and we're thinking that it is 14 miles away, or actually, let me go in the other direction, because this is what she would have done. She would have measured it first and determined, let's do the decimal. This would be 2.8, 2 8/10. 2 8/10 inches is how far it was away. Hold on for a second. My OCD, I don't like that dotting of the I. That's much better. Okay, so how many miles would that be? Well, remember, we can use a couple of different methods. We can look for a giant 1. Actually, let's just go with the giant 1. I'm not quite sure we've spent a lot of time doing cross multiplication yet. So what do you multiply times 1 to give you 2.8? Well, that would be 2.8, wouldn't it? And so if you multiply 1 times 2.8 to give you 2.8, then you have to multiply 5 times 2.8. That's your giant 1 to get our answer for X. And so we'll take our calculator out and say 5 times 2.8 is 14. So X has to be equal to 14 miles, and that's how you use a scale on a map, measure in inches, and then convert the number of inches to a number of miles using proportional reasoning. All right, so let's apply this in a different context. It says Guillermo needs a scale drawing of his house placed on its suburban lot. The lot is 56 feet wide and 100 feet deep. Garage is 20 feet back from the street. All right, so I'm going to do some highlighting. These are the dimensions of the lot. It's a rectangular lot that is 100 feet in this direction and 56 feet in this direction. The garage, this distance right here is 20 feet away from the street. Now, this drawing is not to scale. It's just a brief sketch. I know it's not to scale because when I look from here to here, this is telling me the distance of the width of this garage is 15 feet. But according to the directions, the distance from the garage to the street would be 20 feet, and that's shorter than this. So we know we've got to fix this if we're going to make this proportional. So the directions are use graph paper and a ruler to create a scale drawing of Guillermo's house on its lot. Be sure to state your scale, okay? And it says Guillermo wants you to put a swimming pool. Okay, we'll worry about that later. Let's just focus on section A. So you will need graph paper in order to do this. If you do not have graph paper at home, it's going to make things a little bit difficult. I'll see if I can put up a PDF. Hopefully there's a PDF that you see on Classroom where you can print it off and you can get graph paper from that. We'll see if we can do that. All right, so we have to take these dimensions, and once again, let's write in some of the numbers here that they provided for us. They said the lot was 100 feet by 56 feet, and the distance from here to here was 20. Oops, I'm using the mark, aren't I? 20 feet. Okay, so every one of those marks are feet, they're not inches. So if we are going to decide on a scale, a lot of your graph paper is called, it's 4 squares per inch. And if you've got one that's 4 squares per inch, that actually might help quite a bit. What we need to do is we need to draw this lot so it's proportional. And so if we say 4 squares or 4 units is equal to 1 foot, no, that's not going to work. That means we're going to have 400 of these squares to make that go in that direction. So no, that is not going to work. Maybe let's reverse those. Let's say that 1 square is the same as 4 feet, right? So that means, what is 56 divided by 4? I'm going to use my calculator to figure this out. 56 divided by 4 is 14. Okay, and 100 divided by 4, I know that is 25. So first question is, do I have space on here to create my entire lot? Might make things a little bit difficult. Maybe what I should do is let's make it so that it is, maybe 1 square could be 8 feet. Let's try that and see what we get. If 1 square is 8 feet, then we would take 54 divided by 8 and 100 divided by 8, and maybe that'll make it easier to fit everything on here. I know that 56 divided by 8 is 7, and 100 divided by 8 actually is not the best number. It's 12 and a half, but we can deal with halves. So let's see, do I have 12 and a half here? Can I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? Yes, I can fit that. So I'm going to stick with this scale right there. We're going to see each one of those squares is the same as 8 feet. If you have room on your graph paper to create a rectangular kind of a lot that's properly proportioned to these dimensions, and you want to choose like 1 square is equal to 4 feet or 1 square is equal to 6, probably wouldn't do 6, because then you're going to get a couple of decimals there. Probably 4 or 8 would be the best way to do it. So I'm going to pause and I'm going to create the lot. You go ahead and pause and do the same thing, and you can choose what your scale is, but you probably, I would recommend you do the same as me, just to make things easier for yourself. Okay, so I'm going to pause and come back once I've got the rectangular lot properly proportioned. All right, normally when I do this in class, I actually do the 1 square is equal to 4 feet, and I can go back and forth go up and down, but for you seeing this on a video screen, it's probably easier if you can see the entire lot. So 8, 16, 24, 32, 40, 48, 56. So counting by 8 feet for each one of those squares is 56 feet, and this is 12 and a half of them. I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and a half. Yes, so this is properly proportioned for the size of the lot. Now we need to start putting in the house according to these measurements. So I'm going to start in this corner right down here because I know the distance from the edge of the lot, because the street's going to be right here. Maybe I should write that in. This is the street. I need to get this 20 feet from the edge of the street and 8 feet in this direction. So I'm going to go ahead and place that point. 20 feet is going to be how many of these? 2 squares is 16 feet, and another half of a square is another 4. So if I say, let me use my proportional reasoning here, one square is equivalent to 8 feet, then we need for 20 feet, what do you multiply times 8 to give you 20? I think that's 2.5, so this is going to be 2.5 squares in. And maybe I should be calling them units instead of squares, but I think you get the idea. All right, so let's start with this corner here. It has to be 2.5, and this is 8 feet here. That's 1 square, and so that's the corner of the house. Now I'm going to go this way, and I'm going to go 15 feet in that direction. So 1 square, which is equivalent to 8 feet, is equivalent to how many squares for 15 feet? Oh, goodness, this is where we start running into a little bit of trouble. That's almost 2 squares, right? So what is 15 divided by 8? 15 divided by 8 is equal to 1.875. This has to be 1.875, which, well, I'm just going to have to guess this, right? So 1.875 is probably going to be somewhere around there. That's pretty close enough for what we're doing. So let's start putting in our number lines. And this is going to be the front of the garage. And let's work our way around this way. So this one has to be 17, so that's going to be a little bit further, right? It's going to be 2 point something. So let's take 1 square, which is equivalent to 8 feet, is some number over 17 feet. So what is 17 divided by 8? 17 divided by 8 gives me 2.125. So multiply, remember, these are giant ones. You're multiplying the top number and the bottom number times the same thing. So if I multiply 8 times 2.125 to give me 17, I have to multiply 1 times that. And since we are talking about a unit here, 1 times anything is going to be equal to itself. So that means this has to be 2.125. So I'm going to go 1, 2, and then probably a little bit past that. And then draw my line in. A little bit past it. Is that close enough? Hopefully. Hey, let's get that in there. Maybe, hold on for a second. Maybe I should make these thinner lines to make it a little bit more. Oh, is that already as thin as I can get? Oh, there we go. Okay, that's better. Or is that too much? Maybe that's too much. Let me go to this one. Okay, works. All right, and now we've got to go. How far is the distance from here to here? How can you tell? It's 15 feet from here to here, and it's 30 feet from here to here. So if you take 30 minus 15, doesn't that also have to be 15? And so we're going to take this distance here, which was 1.875, and let's do that again. And I have the ability to clone this, but you don't. So let's see, that's going to be 1, and I'm guessing if I went this far, then it's going to take me there, and then it's going to go to about here, a little bit above there. And I did not choose the right thickness. Let's get the right thickness in there. Okay. Oh, no. I'll fix that. All right. So kind of get the idea. What I would like for you to do now, and we can label this, by the way. I'll label this guy as, this was 15 feet. This was 17 feet. And we know this is 15 feet. And now we've got to get the distance from here to here, which is 38. And the distance, whoa, that is really not scale. If that's 38 and that's 30, not a chance. Okay, so let's go ahead. We're to here now. Let's figure out how many squares you'll need for 38, then how many you would need for 30. And then once we're here, we should just be able to draw the line down and connect it and be done with this activity. Okay, so I'm going to pause. You go ahead and pause and see if you can get the right dimensions there to work your way around, and then we'll finish it. All righty. How does yours look? Let's take a look at the work that we've got here. So we started in this corner, and our scale is one unit or one square has a length of 8 feet. And so if we're counting by the number of squares on this coordinate grid paper, we're going to be always taking the giant one, whatever you would multiply times 8 to give you the distance in real life, you'd have to multiply that number times the 1 to give you the number of squares that you would measure, or the number of units that you would measure here. So 20 feet was 2.5 squares. 15 feet was 1.875 squares. 17 was a little bit more than 2. That was 2.125 squares, so a little bit beyond the 2 there. And then 38 feet, which was the distance here. Oh, this one was the same, another 1.875. And then 38 turned out was 4.75. So, you know, being able to measure that 1, 2, 3, 4, almost 5 units, but 4.75. And then 30 feet was actually a pretty straightforward one, where it was 3.75 times 8 is 30. So 3.75 times 1 means you're going to have 3 1/4. And that's pretty close to, if you go in this direction, 1, 2, 3, 4, it's pretty close to there. 3 1/4 is 30 feet. And then at this point, you didn't really even have to do the measuring, because you knew you were just going to connect the dots to finish the last one to the first one that you started with. But I went and checked to make sure that that made sense. This is supposed to be how many total feet? 38 feet from here to here and 17 from here to here add up to make a total of 55 feet. So 8 times 6.875 is 55. So does this look like it could be 1, 2, 3, 4, 5, 6, and then almost 7, but 0.875? Yeah, that looks pretty close. So we're going to say this is a pretty decent rendition of a scale drawing. Now, the second part of this activity was to add a swimming pool to the backyard. What is the largest pool you would advise him to have installed? This, we're not going to really spend much time doing it. But you see he's got this space here. You know, if you want to do like a whatever kind of shaped pool you want to have, how much space do you need? Do you want a rectangular shaped pool? Do you want a pool that has a waterfall? This is where we get to have fun and art up the picture a little bit. But the idea is, you know, you could fill up that entire space in here, or most of it anyway, and then you could calculate what the area that you have available for a pool in the backyard. But we're not going to do that. Unless you want to draw the pool in, feel free to add pools and gardens and swing sets, whatever you want to add to your drawing. All right, now let's move on to an interior of a house. The scale drawing at the right shows the first floor of a house. The actual dimensions of the house are important. This is 20 by 25. So all angles are right angles. That's important to know, because you know these are going to be rectangulars, and so we're going to use the area formula, base times height, to figure out the areas. So based on this piece of information, what does it say the actual dimension? Oh, that's the dimensions of the garage. This right here, it's not the house, it's the garage that is 20 by 25 feet. So can you tell which one of these is 20 and which one is 25 just by looking at the markings on there? Hopefully you can, because you know the 25 feet has to correspond to the longer side here, which is 1 1/4. So what is the scale of this particular drawing? If you said that the scale is 20 feet is equivalent to 1 inch, that is correct, because this piece of information right there tells you that. So is 1 1/4. I wonder if 1 1/4 times 20, 1.25. 1.25 times 20, is that going to give us 25 for an answer? Yes, it does. All right, so that confirms that our scale factor is 1 inch is equivalent to 20 feet for this particular drawing. Oh, no, don't do that. Don't do that. Okay, so what are the length and width of the living room? So here's the living room. What's the length? What's the width? In real life, you would have to take, all right, so if we know our scale is 1 inch is equivalent to 20 feet, in real life, 2 inches would have to be how many feet? And then for the width, if we know that 1 inch is equal to 20 feet, then what do you multiply times 1 to give you 1.25? Well, we already know that since the garage was 25 feet, then this is the same distance here, that the living room is going to have to be 25 feet as well. So when we multiply 20 times 1.25, we showed that already on the calculator. It was 25 feet. So what is our dimension here? Double the 1 to make 2, so you'll double the 20 to make 40 feet. So the dimensions of the living room alone must be, oh, that's in the drawing. Oh, I've already done both parts. Okay, so the actual would be 40 by 25. Okay, so now for problem solving. If a family wants to lay carpet in the living room and carpeting costs $1.25 per square foot, how much will the carpet cost? So in order to do this, you're going to have to figure out what is the area, the actual area of the living room. That is, if the living room is 40 feet by 25 feet, what is 40 times 25? Go ahead and figure that out. And then once you've got that, then go ahead and multiply the number of square feet times 1.25 to get the total cost of the carpeting. I'll pause so you can work that out. All right, let's take a look and see what we got here. So looking at this, we're going to declare the answer. The carpet will cost $1,250. And how did we get that? Well, because when you multiply base times height, you get 25 times 40 is 1,000, and that's 1,000 square feet because we're talking about area. And since this costs $1.25 per square foot, every square foot times 1,000 is 1,250, right? If you multiply a number, a decimal number times the power of 10, you move the decimal the number of places equivalent to the number of zeros in your power of 10. So you got 3 zeros there, so 1 times 1,000 would be 1,000, so 1.25 times 1,000 has to be a little bit more than 1,000, right? But not more than 2,000. So it seems logical that you would get the answer of 1,250 without even having to do the calculations. But if you did it or used a calculator, that's all right. Now let's take a look, jumping over problem 14 and go to problem number 15. It says Hank is planting his vegetable garden. He has created the scale drawing below. The actual area for the tomatoes will be 12 feet by 9 feet. So all the angles are right angles, and once again, that is telling us that that these are rectangles, and so the area formula will apply base times height. So what is the scale that Hank will use? All right, so what is the known information? We know that 12 feet by 9 feet is this section for tomatoes, which is also 12 inches by 1.5 inches. So how do we figure out what the scale is that we're going to use here? Well, let's start by saying I'll put the bigger measure 12 feet, and the other measure would be 9 feet. And maybe I should put it in the other direction. Hold on for a second. Let's do this so that we can have our multiplier be a scale factor that makes it bigger. So we're going to put the 2 inches correspond to the 12 feet, right? Because that's the longer of the two measures. And then the 1.5 inches corresponds to the 9 feet because that's the shorter of the two. So now looking at this, you can figure out what your scale factor is. What are you going to multiply times 2 to give you 12? And that same number, you should be able to multiply times 1.5 and get 9 for an answer. So I'll give you a chance to pause that for a second. But the second part is if the horizontal length, that's the horizontal length here. Oops, don't do that. The horizontal length of the zucchini plot in the diagram is 5 5/8 inches, then what is the area of the entire vegetable garden in square feet. Okay, so we know that the length is going to be 1.58, and so we're looking to find the entire area of the vegetable garden. So you go ahead and pause and answer question A, and then work through part B, and I would highly recommend that you copy this diagram into your journal with all the labels and all the measurements, and then answer B. And when I when I stop pausing it, when I start playing again, we'll have a reveal of the answers, and hopefully you'll have the same answers as me. Alrighty, let's see what you got. So for the first part, what scale did Hank use? Well, if we're taking a look at this, we're seeing that when you multiply 2 times 6, you get 12, and so we'll multiply 1.5 times 6, and we would get 9. So that means that every inch must be equal to 6 feet, right? Because 2 times 6 is 12, 1.5 times 6 is 9, so every inch on here is equivalent to 6 feet. So if the zucchini patch is 1.5 inches, then we're going to have to multiply that times 6 to figure out what is the distance in feet. So using, you could use a calculator, or we could do our fraction operations. When you multiply 6 times 1 5/8, you're actually multiplying it times 13/8, and 13 times 6 is 78, 8 times 1 is 8. 78 divided by 8 ends up being 9 3/4, or 9.75. So the zucchini section is 9.75, and we have to add that to this dimension of the tomatoes, which up top said it was 9 feet wide. So that combines to make 18.75, and then the distance across was 2 inches, so that's the same as 12. So we're going to use the area model to multiply 18.75 times 12. And what is 18.75 times 12? Turns out it is 225 square feet. So this entire garden, once we have converted from inches to feet in real life using our scale factor of 6, and proportional reasoning, we get an area of 225 square feet. All right, so this is the basics for how you use a scale factor as a multiplier to help us with our proportional reasoning to figure out distances. Once you know the scale factor and you know one distance, maybe a distance on a map, you can figure out the distance in real life by using proportional reasonings and your giant one with that scale factor. All right, so let's go ahead and head off to our next activity. Take care.
Hey, feeling good, like I should. When in dark, I walk around the neighborhood. Feeling blessed,